So thank you very much for listening to my presentation today. Just want to say that I'm very appreciative of being able to present this work to all of you today. Now, my talk today is based on the open access research paper that was published in May of 2023 with the title available on the screen. And this project was conceptualized and spearheaded by Maria Pilar de Lara Castells from the CSIC. I would also like to just thank and acknowledge my PhD supervisor, Ludmila Moskaleva, for her help and support throughout this project. Now, atomically precise metal clusters have emerged in a variety of fields with various applications in luminescence, energy conversion, catalysis, and so much more due to their unique properties and quantum confinement effects. An example of an AMC would be copper clusters of size less than 10 atoms, such as copper-5 clusters, which were used in this study. Now, in terms of copper-5, Pilar has been doing predominantly research now for the past 6 years on these copper-5 clusters and has produced quite fascinating results and studies. And I'll get to that in a moment. But first, when we look at a metal such as copper at a size, let's say, less than 1 nanometer, at this scale, there's geometric and electronic property changes that occur due to quantum confinement effects, and the metal band structure is broken with a series of discrete electronic levels being formed. Now, at a size this small, there's unique properties that arise for the copper clusters versus the bulk copper. And as we decrease the size of the copper cluster even more, we get copper-to-copper connection, so the distance between them being about 1 to 2 angstroms. So that's equivalent to a typical bond length. Now, in terms of the work that Pilar has done on this topic, she has shown that copper-5 clusters can form complexes with oxygen molecules. And at this point, there's also a charge transfer that occurs with the copper-5 clusters becoming positively charged and the oxygen molecules becoming negatively charged. And once the oxygen molecule is released, the copper-5 cluster becomes or goes back to its metallic phase. She also showed that copper-5 can, or rather she studied copper-5's ability to capture CO2 with a role in looking at breaking the CO bond in CO2. And she did this unsupported and supported on titanium. Then she also looked at copper-5 and how it alters the absorption properties of titanium. Now, in terms of work that's more relevant to this study or this presentation today, she has shown that copper-5 clusters can sinter into larger nanoparticles in the gas phase, and that the individual copper-5 clusters in this larger nanoparticle maintain their original properties. And more recently, she has shown that the trigonal bipyramidal geometry of copper-5 is a distorted Jahn-Teller fluxional molecule, and suggests that this property is what helps it interact with environmental molecules. So as you can see, these copper-5 clusters have various roles and uses and properties. And to sometimes get the full use out of these properties, the AMCs have to be supported on solid support systems. But it's on the same solid support systems where the clusters can end up sintering into larger nanoparticles. Now, in the event that you don't want the sintering to occur, perhaps you want to keep the AMCs separate so that you can ensure that whatever you need to use these AMCs for, you can, because perhaps the larger nanoparticle doesn't maintain the properties and uses as the smaller clusters do. And so you'd have to look at an alternative support system, such as, let's say, graphene with defects. And the proposal here is that the copper-5 clusters would fall into the vacancies and get stabilized there. Now, in terms of our models used, copper-5, particularly planar copper-5, was used as our AMC, while we use graphene to look at the dimerization and the stabilization of the copper-5 clusters. Now, graphene is atomically flat, chemically inert, has a large surface area, and all of this makes it a great support because it's not really expected to influence the copper-5 cluster's electronic properties so much, especially if it can confine it. Now, in terms of pristine graphene, we looked at the dimerization on it. while we did the stabilization study on defective graphene. And altogether, we used our graphene sheet as a 6x10 supercell. Now, our study can be split into two parts: electronic structure calculations and AIMD simulations, ab initio molecular dynamics. And in terms of the AIMD simulations, we used periodic DFT-D3 calculations. And so to make sure the results that we're getting are reliable and good in a way, we want to compare it to more accurate post-Hartree Fock methods. And so in this work, we used the VASP simulation code for the static DFT-D3 calculations. And we compared it to these more accurate methods using a bunch of different basis sets. And since we performed the AIMD simulations using a different software called CP2K, because it's faster and more efficient than VASP, at least VASP version 5, we also need to show that there's a good agreement between VASP and CP2K. So in terms of the DFT-D3 settings, here are some that we used for VASP and CP2K. While here's some of the AIMD settings we used for CP2K. And these different settings and parameters were used because it offers a good balance between accuracy and efficiency. Now, in terms of our electronic structure calculations, as I mentioned earlier, we wanted to show that there was a sensible agreement between the DFT-D3 calculations and the more accurate post-Hartree Fock methods. And this work was done primarily by Pilar. And we ultimately do see that there's a sensible agreement in terms of the copper-to-copper bond lengths and the relative energies across various methods and basis sets. We also showed that the displacement between the more accurate method and DFT-D3 are quite similar. We showed that the planar copper-5 cluster is low in energy than the trigonal bipyramidal geometry of copper-5, at least in the gas phase. We also showed that the D-to-D symmetry of copper-10 is low in energy than other planar-based copper-10 dimers that we studied, like the ones you see on the right-hand side of this slide. And then we also observed that the copper-5 clusters interact weaker on the support of graphene than when they're left unsupported. Now, before I get into the actual AIMD simulations, I thought it would be a good idea to first look at the dimerization and the stabilization of copper-5. And I'm going to be using a real example here from the particular work we did. And so this is the later part of the particular simulation, and the two copper-5 clusters are adsorbed on the graphene sheet. And in terms of dimerization, the copper-5 clusters would be attracted towards each other. So they aggregate, they join together to form a larger nanoparticle. And so in this process, we can see how the sintering would look of the copper-5 clusters on graphene. Now, in the event that you want to keep the copper-5 clusters separate, you can look at the stabilization of the copper-5 clusters. And here we have the copper-5 clusters on graphene with two vacancies, as you can see over here and over there. And when we perform or look at the particular simulation, the hope is that the copper-5 clusters would be more attracted towards the vacancies than each other to form the dimer. And so for safety reasons, it would be a good idea to have multiple vacancies available to decrease the likelihood of a dimer being formed. Now, in the gas phase, we already see the copper-5 clusters sinter. So if we can find a method to prevent that, if we want to prevent it, then we present here a potential way of doing that. Now, the first AIMD simulation I would like to look at is the dimerization of the copper-5 clusters on pristine graphene at 400 Kelvin. And as you can see, initially the copper-5 clusters are at least 8 angstrom apart, and eventually they end up forming this dimer. And this happens in 3 steps. The first step is that the copper-5 clusters diffuse, so they move apart and they rotate about, as you can see there. And then eventually they are attracted towards each other and they aggregate to form this planar-based copper-10 dimer here at 51 picoseconds. And the last step is that the individual copper-5 clusters in this dimer undergoes a geometric change from planar copper-5 to trigonal bipyramidal of copper-5, as you can see at 111 picoseconds. And this eventually forms the D-to-D symmetry of copper-10. So after finishing the simulation, we did further analysis of the MD frames. And we did this through looking at the root mean square deviation of the copper-5 clusters. So this tells us how much the copper atoms are displacing over time compared to some initial frame. We're also looking at the minimum carbon to copper distance and the minimum copper to copper distance over time. So in terms of the minimum copper to copper distance, on the left-hand side, we have the intra-cluster minimum copper to copper distance. And as you can see by this dotted line, this is where the dimerization starts to occur. And there's this faint increase in the minimum copper to copper distance. When we look at the intercluster minimum copper to copper distance, there's a sharp decrease close to the dimerization event, and then it's just fluctuating about. It's not really changing much anymore. So even if we didn't have the frames available, this particular plot here would be a good indication of the dimerization occurring. Next, we have the RMSD. And you don't have to really look at all the lines that you see here. The most important part would be when you see the lines are overlapping a lot and they follow a similar trend, that's a good indication of translational motion. And here we see that the lines are quite far spread out, but they follow a similar trend. That's a good indication of rotational motion. And so you can see cluster 1, which was on our left-hand side, is not really experiencing much mobility. So it's not translating and rotating much up until the dimerization event. And then for cluster 2, the one on the right-hand side, initially it's translating a lot, then experiencing quite a bit of rotational motion. And then the dimerization event occurs. And after the dimer is formed, there's quite a bit of translational and rotational motion. Then we have the minimum carbon to copper distance. And as you can see, after the dimer is formed, there's this increase in the minimum carbon to copper distance. So this shows that the dimer is lifted further away from the graphene sheet compared to the individual copper 5 clusters, which nicely ties in with the copper 10 dimer binding weaker to the graphene sheet compared to the individual copper 5 clusters. Now, we also did the simulation at 300 and 600 Kelvin, and we used constrained and unconstrained graphene. And for all of these different temperatures and methods, we found a very similar result for the dimerization. So you can see here for 600 Kelvin, we also started at least eight angstrom apart, and eventually the dimer is formed, and it also goes according to the 3 steps that I mentioned earlier. The slight difference here is that the simulation is significantly faster, and there's this, I would call it, I guess, pseudo geometrical transformations that occur for the copper 5 clusters. So next we can look at a comparison of the minimum carbon to copper distance for the 400 and the 600 Kelvin run. And in general, the trend is quite similar. We see an increase close to the dimerization event for the 400 Kelvin run. And this line here at 18 picoseconds is not where the dimer is being formed. It's some other event, but closer to the dimer event, we see there's this increase. Then we have the minimum carbon to copper distance, and it's a similar story here that as the dimer is being formed, the minimum carbon to copper distance increases for all of them. And then we have the intercluster minimum copper to copper distance. And at first glance, it might seem like there's a big difference between these plots. Like for the 400 Kelvin, you have this section here where there's this big drop in the distance, while for the 600 Kelvin, we have this intermediate phase where it's closer to each other, the clusters, but haven't formed the dimer yet. But if you look at the 400 Kelvin run, you see this peak here. And this is quite similar to this massive peak that you see on the right-hand side. And the reason it looks so much smaller is that the time scale on the left-hand side is much bigger. So it's more than twice as long, the simulation. And then we have the RMSD comparison. So here we see the biggest difference between the 2 simulations. And that is that in terms of the rotational and translational motion of the copper atoms, it's more at the 600 Kelvin run than the 400 Kelvin run. So the copper atoms are more mobile at the higher temperature, which makes sense. So the next particular simulation I'd like to look at is the stabilization of the copper 5 clusters on graphene. And this was done at 400 Kelvin. And so we see that the copper 5 clusters are quite a bit of a distance away from each other, and also these 2 vacancies. And each vacancy has 2 missing carbon atoms. This type of vacancy is more stabilizing than the vacancy which has only 1 carbon atom missing. So you would expect to see the double carbon vacancies more often. And so initially, the vacancies are closed. And when the copper 5 clusters get close to the vacancies, the left one gets there first. It falls into the vacancy, so the vacancy opens up, and then it quickly undergoes a geometrical transformation to trigonal bipyramidal, and is just rotating around inside of that vacancy. The other cluster, cluster 2 on the right-hand side, also gets to the vacancy eventually, but it doesn't go into the vacancy. It just ends up optimizing as a trigonal bipyramidal geometry and is rotating above the vacancy. So we can compare this to the constraint simulation, where we actually see that because we have now fixed all the carbon atoms and left the vacancies open, that both copper 5 clusters end up going into the vacancies, and they optimize to form this trigonal bipyramidal geometry inside of the vacancies. So if we do an adsorption energy comparison, we can see that when both clusters are confined in the vacancies, the adsorption energy is lower than if only one of them is confined, and this is significantly lower than when none of them are confined. So how we ended up starting with. And so if we do a further analysis of the MD frames for the unconstrained simulation, we see that as the copper clusters get to the vacancy, there's this increase in the minimum copper to copper distance. And for the inter-cluster minimum copper to copper distance, there's this decrease over time. So as the clusters are confined in or at the vacancies, we just see this fluctuation of the minimum copper to copper distance intercluster wise. And I ran the simulation for even longer, and it just keeps fluctuating like that. And that's because the clusters are rotating in or on top of the vacancies. Then we have the RMSD analysis of this particular simulation. You can see the cluster on the left-hand side, so the left cluster is displacing quite quickly to get to the vacancy, and then it just undergoes rotational motion as it's now trapped in the vacancy. Compare this to the right-hand side cluster, which takes a bit more time to get to the vacancy, and then it experiences this rotational translational motion as it is rotating over a larger area on top of the vacancy. And finally, for this particular simulation, we look at the minimum carbon to copper distance. And as you can see, as the clusters get to the vacancy, there's this decrease in this distance. Interestingly, the cluster that is not confined into the vacancy has a shorter minimum carbon to copper distance. And so that wraps up my talk today. So we ended up showing that planar copper 5 is low in energy across multiple different methods and basis hits compared to some other geometry like trigonal bipyramidal. We showed that the D2D symmetry of copper 10 is low in energy than other planar-based copper 10 dimers. And we showed that copper 5 clusters dimerize on pristine graphene, while they end up being individualized and stabilized at the defects or the vacancies on graphene. Pilar and Ludmila would just like to acknowledge and thank the following, and I would like to acknowledge and thank all of you for listening to this presentation. Thank you very much.